Welcome to Electrical Fundamentals, ENGI 12578. My name is Mohammed Abdullah. I will be your instructor in this semester. This is lecture 1, and in this lecture we will just explain you some of the guidelines for this course, and we will discuss a bit the different notations, the scientific notation, the engineering notation, and the SI units that we will consider. And that should be it for today's lecture. So as we said, the name of the course is Electrical Fundamentals. And if you're in this class, it's because you're either in the Computer Engineering Technician or Technology program, or in the Electrical Engineering Technician or Technology program. The semester will go from September the 14th until December the 18th. In general, we should have 14 weeks, but this semester, because of some of the delays due to COVID, we will in fact proceed with 13 weeks, but we will adjust the lecture accordingly. This is a 4-credit course. This semester, I am the only instructor that is teaching this course, Electrical Fundamentals. And so if anybody at Sheridan is taking this course, you're all taking it with me. I'll be teaching both the lecture and the lab. And we will also have tutorials, or if you will, peer assisted learning, PAL sessions, where a senior student will guide you with extra problems and questions. So you have the schedule here for who is who, and you can see it just here below. Probably you already learned that we will post everything on SLATE, but I'll mention it very quickly. So we will use Sheridan's Learning and Teaching Environment, SLATE, regularly to post all that is related to the course. So you simply need to go to the link that is indicated here. And you look for this course, and once you go there, you'll find the main landing page. I'll be posting all the course materials, the slides, the videos, the recording of the live sessions, announcements, all in here. And also, if you need to send emails to me, please use the email through SLATE, not my own personal Sheridan email that you can find on my website. Now, in regards to the lectures, we will mostly, in fact, we will have all the lectures in live sessions. So they are as scheduled on your calendar. So we'll have that there. But in addition to that, I will do my best effort to post a recording of the lectures on YouTube. So for YouTube, you could always be advised of when a lecture is posted. You could subscribe if you want, and the channel that I'll post it has the following link. So you could go to this link and then keep track of it or subscribe to it, and then you'll be notified when new lectures are dropped. We will kind of do both the live sessions and the recorded approach, so synchronous, asynchronous teaching. And the reason is that we want to apply a flipped classroom approach, so that students will be able to see the lecture before the session, and then in the session we will do more problems and discuss what you saw in the videos, or you could come in with your questions. If you have any questions, or you need to be in contact with me for further inquiries or details, or if you have some concern, you could always send me an email. And like we mentioned before, the best way to reach me is by using the email that you have on SLATE. So you could go to SLATE and send me an email there. In addition to this, you could also book an appointment during dedicated office hour days and times. So my office hour this semester are on Monday, Thursday, and Friday. So Monday from 2 p.m. to 4 p.m., Thursday from 12 p.m. to 1 p.m., and Friday from 11 a.m. to 12 p.m. So if you need to not necessarily send an email, but you want to in fact talk to me, just propose a date that would work for you and a time, and we'll give you a 10-15 minutes for discussion. You really have to request an appointment before, in fact, having a session to discuss your matter, because I have some 110 students, and it would be messy without doing it with this approach. So for the grading scheme that we will apply in this course, you'll find more information in the class plan that is posted on SLATE. So it's a 4 or 5 page PDF document that I strongly encourage you to read. But in general, these are the different evaluation items that we will look throughout the semester. So as you notice, there is a 20% dedicated for labs. We will have 10 labs. Every lab is worth 2 marks. And you'll have 2 days to submit your lab report. So we'll discuss on that later on. We also have lab tests. So in the first half, we'll have the first lab test, which is based on what you saw in the labs in that period. And in the second half, we will have another lab test. And the lab tests are based on simulations that we will use using Multisim. We will also have 3 quizzes, and that's also kind of a way to prepare you for the big evaluations, which is the midterm and the final. So if you look at the grades, the highest grades are really dedicated to the midterm and the final, and of course the lab test as well. And then the quizzes and the labs each they have smaller amounts, smaller weights, but in the aggregate they all add up. So I think it's important to seize the opportunity and to get as many marks as you can from different areas. One thing that you should be mindful of in this course is that in order to pass, you need to really pass the following 4 conditions. You need to pass this condition. So the exams, you need to get at least 25 out of 50 in the exams. You need to pass the lab test. So you need to get at least 10 out of 20 in the lab test. You also need to pass the lab work. So you need to get at least 10 out of 20 in the lab work. And overall, if you add everything, you need to get 50 or above. So if all the 4 conditions are met, the exam condition, the lab test condition, the lab work condition, and overall greater than 50, one would pass. Otherwise, if any of these components is not a go, then students would fail. So it's really strict to make sure that you really are proficient with all the different components. So I think this is very important. So just be mindful that if at the end of the semester you get, I don't know, 52%, this doesn't mean that you will pass the course. Having a grade above 50, overall grade above 50 does not mean that you pass the course. We really look at each of these components. Okay, so 4 conditions to meet in order to pass. The evaluation is closed books. You're allowed to use calculators, and you should also monitor your own progress. And I think it goes without saying that grade is not negotiable. You get the grade that you deserve. The textbook that we will use is this one here. So it is from Floyd and Bushlaw. So Floyd is a famous author with Bushlaw. So they produced many of these educational books in electrical engineering and in basic circuit analysis and in electronics. So this is the one that we will use. So it's called Principles of Electrical Circuits, Conventional Current version. So this version is from 2009. It's the 10th edition. The publisher is from Pearson, and I think it costs around 200 Canadian dollars. You could also get a soft copy of this book. It cost about 53 Canadian dollars. And to get the soft copy, this is the website that you could go to get it. This is if you will, a select chapters of the book that you will have with this package, and it's only available for 6 months. So this is something that was done by professors from Sheridan, where it was various chapters from the book were selected, and it was organized with the publisher. And so you won't get all the chapters in the book, only the ones that we will need for this course. And like we said, it will only be valid for 6 months. So I think if the price is too high, this could be a good option. If you are a computer engineering student, maybe this might be the best option. Getting the book may be a bit too excessive, but if you are an electrical engineering and electronic engineering technician technology students, maybe getting the book is a better option for you, because you have 3 other courses where you will also use the same book. So you'll use it in electrical fundamentals, this one here. You will also use it in electrical circuit principles, this one, and you will also use it in electrical circuit analysis, this one. So all 3 courses will use this, and that perhaps could be a good option to in fact get the actual book. But I'll leave it up to you at your discretion to decide what to do here. So in the course, we will focus mostly on DC circuits, as you see here. We will also introduce some parts of AC circuits in the near the end of the course, but the focus is mainly on DC. And the chapters that we will cover from the book are chapter 1, 2, 3, 4, 5, 6, 7, 8, 11, and 12. We're not going to go directly in that sequence. We might just jump in different sections. I'll give you a breakdown of that in a weekly schedule shortly. But these are the key chapters that we will cover. So we will look at voltage, current, resistance, Ohm's law, energy, power, series circuit, parallel circuit, series parallel circuit. We'll talk about superposition and Thevenin approaches to solving circuits, and we will introduce you to AC at the end. We will also discuss capacitors as well. We will mainly focus on passive components as opposed to active components, but I think that kind of gets you ready for the more advanced courses. The assumption here is that this is your first course in electronics, and that's why we will take you through the fundamentals. Many of the concepts here are perhaps things that you've already saw to some extent in high school or before coming to college, and hopefully we will build on that. But otherwise, no worries, we will build the skills gradually. In regards to the lab, we will have 10 labs as mentioned earlier. Each is worth 10%, and that adds up to 20%. All the labs are conducted individually. We will, for some courses, by the way, at Sheridan, some students have the access to go on campus while respecting physical distancing and all that. But for this course, we will in fact conduct all the work using simulation tools. So we're not going to be in a lab environment. Typically, this course is in a lab environment, but for now, we will do it using simulations, and we will mainly rely on Multisim Live. We'll talk about Multisim Live in Lab 0. Lab 0 is just the lab that we will see in the first week, and there's no grade. It's just to make sure that you not install, but rather register with Multisim. Multisim, by the way, I should mention that it is from this company, National Instrument, the Texas company in Austin, and that's what we will use for all the simulations that we will do. The approach for the handout for the lab is that it will be posted before the lab on SLATE. So when you do the lab, you'll be able to access that. And then for the report, for the lab report, you will run a simulation of your circuit using Multisim, and then you could take a screenshot of this and then append it on your lab report, and then upload the PDF version of your lab report to SLATE. And of course, like we said before, you have 2 business days to do that. So let's say if you have a lab on Thursday, you will need to submit it by Monday 5 p.m. So business days does not count the weekend. These are the labs that we will do, and as you see, there is some match to the different topics that we will cover in the lecture. Now, the following might be one of the most important things that you will find in the class plan. Of course, everything in the class plan is important, but this is a good summary of what you will do in the semester. I usually put a a picture of this on SLATE on the first page, and I strongly encourage you to come to it on a regular basis just to know where we are and where we're heading. So you have the different weeks here with the dates. You have the different lectures that we will cover, the topics. And you also have the different lab work that we will do. You also see in blue all the different evaluations that are sprinkled in different places. I also listed the reading that we want you to read for each of these weeks, so you'll have it here. So you have the chapter and the sections. Now you should realize that small variations from this timetable are normal. Sometimes we have to go with the pace of students, and sometimes there are some unforeseen circumstances. So this timetable could change, and we'll just work with that. So this is a common thing that you should know in regards to missed evaluation with our department, with the mechanical and electrical engineering department, is that if any evaluation item is missed, the responsibility of the instructor, the professor, is to give a 0. And the 0 can be removed if you can justify why it was missed. Now, if it is an emergency, something happened and it's an emergency, you need to contact the department within 48 hours, within 2 working days. So the ways to contact them is either through this phone number or this email. If it is a non-emergency, and for instance, you know in advance that you're going to miss that lecture, then you need to contact the department a week before the day that you're going to miss it, and just make the arrangement. And once you contact them, there's a bunch of formalities that you have to go to. You have to fill a missed evaluation form and so on. So please just be mindful of that. So if you get a 0, don't be upset at your instructor. These are just the guidelines that we have to follow. If you can justify it, the grades will be removed, and the approach to figure out what to do will be discussed with the instructor. So as Sheridan, we take academic integrity very seriously, and I think you should realize that all submitted work that you do must be originally performed by you, the student. Midterm quizzes, final exams, labs must be performed individually, so it's not a group work. It's not something that you could take from others, and any academic integrity violation will be treated very seriously. So I think this you need to kind of realize, and you could in fact get familiarized with the policies that are used at Sheridan by going to this link. You'll find more information. Now, because we're doing all the evaluations online, we're not meeting face to face. There are 2 mechanisms that we will use to deter students from plagiarizing: Respondent's Lockdown Browser and the Respondent's Monitor. So if you hear these things, you should know what they are. You'll use them with different courses. Respondent's Lockdown Browser, what it does is that it will basically lock down your browser. You won't be able to check your email or go to any search engine to look for information until you finish the exam, and then your screen will be back to what it was before. And then Respondent's Monitor is that in addition to this, you will have a camera that will monitor you and record your performance as you go throughout the evaluation. Now, in this course, after some discussion with the course lead, we decided not to use Respondent's Monitor. So we won't use this webcam process for checking academic integrity. We will only use Respondent's Lockdown Browser. So that's just for that, but I still wanted to show you in case you see it in other courses. My objective in this course is to guide you technically to understand the basics of electrical engineering and circuit analysis. And your objective is really to learn the engineering fundamentals and to connect what you learn to real-world applications. So we hope that you please take the lectures and labs seriously, and you try to absorb as much as you can. So now you're admitted, you'll be spending a few years here, you'll graduate, and then eventually hopefully you get a good job, and hopefully everything that you learn here will be added to your toolkit. So as you perhaps are watching this lecture and you look around your surrounding, you could perhaps attest that everything that we have in our daily life has some form of operates based on electricity. In fact, all modern systems are electrically operated using either DC or AC sources and circuits. From your smartphone to the internet that you have, the servers, to modern vehicles, electric vehicles, connected vehicles, satellite systems, aircraft, industrial automations, and others. These are just some examples, and as you notice, they all operate on some form of an electric circuit. And so understanding the electricity is extremely important. It's like the air that you breathe. To understand electricity, it's very complex. Electricity is abstract. One cannot see electricity. You could only see the effect of electricity. So we'll see how we make sense of it by learning the essentials and the fundamentals in this course. So in this course, as noted earlier, we will focus more on DC circuits. So DC stands for direct current, but we will also see AC circuits. And I wanted to kind of show you in a brief slide how they differ from each other. So in this case, you have a passive component, a resistor. You also have a passive component here, and you have a DC supply, a DC source. It's just like a battery. And here you have an AC supply, an AC source. It's a sinusoidal. It could be other type of signals that bring energy to your source. This is an alternating because the voltage changes polarity from positive to negative, and that's why it looks like this. So this is a sinusoidal, and that's how the voltage would work with time. So as time goes, it kind of fluctuates between positive and negative in this format in an AC circuit. In a DC circuit, as time goes, it remains flat at a certain level, let's say 5 volts or 10 volts or 3.3 volts. And of course, as the time goes for a long time, let's say a few weeks or months, and you keep it operating with a DC source and you don't recharge, of course this will drop until it dies, and then when it dies, then you recharge the battery or you replace the battery. And so that's kind of the how the source itself looks like in the time domain. In addition to this, maybe I should also show you how the electron moves. So when you have a source, you have electrons that will start flowing in the conductor, in the wire. So so you could think of current flowing in this direction. In fact, electrons flow in the reverse direction of current, but for now, let's just consider electrons flowing in the same direction of the current. So let's just consider electrons flowing in this direction, or to be more accurate, let's consider the current flowing in this direction. It goes through the resistor and it goes back into the source. So it always goes in one direction. As you see in this picture, the current is going to flow in in this format, right? So in a clockwise format. Whereas in the other, within AC source, the electrons will flow in this path in clockwise, and then suddenly they flow the other way. Right? So they move this way, and then they move the other way. So they move to the right up to certain time, and then they stop, and then they move back to the left. So they alternate, and that's how you get this effect of an alternating current. You'll see more of this once we reach AC circuits and more advanced courses on AC circuits. Now, in terms of analysis, AC circuits are more complex. They're harder to analyze. DC circuits are perhaps considered easier to analyze because the time factor is not necessarily there. So here, time becomes more important because it varies with time much faster than with here. Here, it will still vary with time, but after a very long time, you'll see some effect. But otherwise, if you look at it momentarily and in short times, time is not very critical with DC circuits. So therefore, DC circuit analysis with DC circuits is much easier than with AC circuits. And therefore, if you will, this course is kind of considered easier than courses where the focus is more on AC circuits. So these are some examples of what you will see with a DC circuit. So basically different type of supplies, DC supplies like batteries. And so this is a battery of a vehicle. This is the battery that you have in your watch and other type of batteries that you have. Whereas here you have the AC supply that you perhaps get from the wall. So if you're in North America, the voltage that you get from the wall is 120 volts. And if you're, let's say in Europe, it would be anywhere from 220 to 240 volts. Here in North America, it's 60 hertz, and in Europe, it's 50 hertz. As well, the way that the plug will be different as well from different parts of the world. So any of these different adapters that you have, these are basically what it does is that it takes from the wall AC, and then what you get when on the end that is connected to the computer is you get it in DC. So all electronic components operate on DC, but they are fed through AC. So you get it through AC, it goes through through the power supply, it changes the AC to DC, and what is fed to your machine is a DC source, and that's how your equipment is charged. The same thing is with your cell phone, which you get from the wall when it's connected to the socket. socket, you're getting an AC voltage. You charge, you put it to your device. In the device, the AC is converted to DC, and that's how your device is charged. And then you unplug it from the wire. So I hope that kind of gives you some sense of the difference between DC and AC. It's a very quick overview of it. So in terms of courses, you'll see DC mainly in this course, and in these two advanced courses you'll see AC, and they are prerequisite of each other. These courses are for electrical engineering students. Computer engineering students, you guys won't do this. You will just basically stop it here and then see more advanced courses related to this, but you won't take these two courses. So this part is not really part of the curriculum of the course, but it is something that we've noticed with students, is that sometimes they perhaps have forgotten the difference between scientific and engineering notation, and it's very critical to know the difference between both of them, and particularly to pay attention to engineering notation. You're engineering students, and you should learn how one would represent results in engineering notation. So we'll go through that very quickly here, and hopefully it's a good refresher to your mind. So let's say you're given a number, and you look at this number, there are many digits, and if you say, what is this number? This is 47 million. And if you were to represent it in scientific notation, it has to be represented in the format of a times 10 to the b, where a is a value anywhere greater or equal to 1, but less than 10, and b is essentially an integer. Now, this is an integer. It could be a negative or positive, but it's an integer. So if you move into the various decimal places, you move by 1, 2, 3, 4, 5, 6, 7. So you'll have 4.7. This is the value of it, times 10 to the 7. You move to the left, so therefore you would write it like this. This is a scientific notation. In engineering notation, it's the same rule. Essentially, you represent a value, and it's still, you have to represent it in the format of a times 10 to the b, where a is a value that is equal to 1, but less than 1,000. So now you have a greater range for A. And in addition to this, you also need to make sure that the value for B is a multiple of 3. So B can only be multiples of 3. So a 7 here would not work in engineering notation. It is not a multiple of 3. So it has to be, let's say, I don't know, -3 or 0. 0 is a multiple of 3, or 3 or 6 or 9. So it has to be multiples of 3. So if you change this to a multiple of 3, you could make it 10 to the 6, and then the 4.7 would be multiplied by 10, so it becomes 47. So this would be an engineering notation format. It meets the rule. A is a value between 1 and less than 1,000, so that's true. The B is a multiple of 3, and that's true, and therefore this is an engineering notation. Let's do another example. So we have this one here. This is a small number. We could represent it in scientific notation by moving to the right. So by 1, 2, 3, 4, 5. So we could write 2.7 times 10 to the -5. We move to the right, therefore it becomes minus. And if we were to look at this, this certainly is scientific notation, but is it engineering notation? The answer is no, because this is -5, and -5 is not a multiple of 3. So one way to make it in engineering notation would be to make it -6. So -6, you would basically multiply by 10 to the -1. But because you multiply by 10 to the -1, you need to also get rid of it. So you multiply by 10. So 2.7 multiplied by 10 becomes 27. And this is 10 to the -6. Now this is engineering notation. It meets the rule for engineering notation. This is a multiple of 3. And this is a value between 1 but less than 1,000. Now you might also say, well, why don't I put it 10 to the -3? 10 to the -3 is also a multiple of 3. But if you do 10 to the -3, then what you do is you'll have times 10 to the -2, and this becomes 0.02. So this becomes smaller than 1, and therefore 10 to the -3 would not work. The only one that would work is 10 to the -6, and that meets the rule for engineering notation. This is another example. So here we look at this value. We want to represent it in scientific notation. The value has to be anywhere between 1 but less than 10 in scientific notation. So we move by 1. So we write 6.05. We move to the right, so we could just write times 10 to the minus 1. In engineering notation, this cannot work. It's not multiple of 3, so we can make it multiple of 3. We could do minus 3, and then we could multiply by 10 to the 10 to the 2 to deter this. So you move by 2, and this is the result that you get in engineering notation. Also, I should mention that with a calculator, you have usually a button where it says ENG, and that will essentially change any value that you get in engineering notation. So this is very important to learn this part. For us, when you do anything in the lab or in the exam, always represent your result in engineering notation, not in the scientific notation. To communicate sciences in engineering, we will always use some of the fundamental units that are provided to us through the SI units. SI stands for the Système International d'Unité, or the International System of Units. And essentially it gives us like different conventions that are used in identifying various quantities. So if we talk about length and we are referring to the standard in scientific communication, length will always be represented in meters. So that's the symbol of it, meters. If we talk about mass, mass will be represented in kg, in kilogram, not in pound. Pound is something that is used perhaps in North America and mostly in the US and other places, but it is not a scientific way of representing it. So if you look at a scientific document or a book or a publication, it has to be used. We basically use the SI units. So pound is not an SI unit, but kilogram is an SI unit. Time would be in seconds. So seconds is an SI unit. Anything else, hour is not an SI unit. Sometimes we use hour just because it's easier for certain comprehension, but the SI units requires that we use measure of time in seconds. The electric current is measured in amps. In temperature is not measured in Celsius. It is not measured in Fahrenheit. It is always measured in Kelvin. So if we talk about scientific communication, for temperature, it should be represented in Kelvin. Now, how do you differentiate? How do you move from Celsius to Kelvin? You just add 273 to Celsius, and that gets you the result in Kelvin. So these are some conventions of the SI units that you should be familiar with. What is interesting here to note is that amps is the only quantity in electrical engineering that is part of the SI units. Everything else, voltage, resistance, and so on, it's not part of the SI units. They are derived from other quantities from the SI units. Okay, and we'll see that on the next slide. Now, in electrical engineering, we will use typical quantities on a regular basis, and the ones that we will use a lot in different courses and in different areas of our discipline are essentially current, voltage, resistance, and power. So if we talk about current, the unit of it is amperes, and the symbol of it, so usually people don't write amperes, they just write the symbol, they just write A. So you could just say it's 5 amps. And when you write it, if you look at specs of different equipment, they just write 5, a space between 5, and then they just write big A. So big A essentially stands for amperes. Voltage. The unit of it is volt, and when you write it with specs, let's say you want to say 3.3 volts, you just write 3.3 space and then you put V for voltage. Resistance is the unit of resistance is ohms, and when you write it as a quantity, you just write like this, the omega symbol, the Greek omega symbol. So let's say you want to say something is 1,000 ohms, so you would basically write it in engineering notation, and you would write 1 kilo ohm. So 1 space K, small k, and then ohm, this thing here, this symbol, this Greek symbol. Power is in watts, and the symbol for it is W. So, please, I'm sure this is a review of something that you've seen in the past. Now, alongside engineering notation, we also have to see engineering prefixes. So we typically use engineering notation, and then these 10 to the b, or 10 to the, where b is a multiple of 3, we don't necessarily write it as 10 to the multiple of 3. We write what it, the equivalent of it, the prefix of it, the engineering prefix of it. So if you have a value that is, they're all multiple of 3, and these are large values. So if you have a, let's say 10 to the 3, we usually just write k for kilo, and k basically represents 10 to the 3. We write M for mega, and that represents 10 to the 6. We write G for giga, and that's 10 to the 9. We write T for tera, and that's 10 to the 12. And then we write P for peta, and that's 10 to the 15. So I'm sure you've seen this in different areas, but this is just kind of a reminder. So I don't know, some examples here. Let's say your Wi-Fi technology, it operates at 5 gigahertz. So you would just basically see 5, big G for giga, and then the symbol hertz, HZ, and then gig essentially means 10 to the 9. So you could also say that it is 5 times 10 to the 9 hertz. Mega, you will also see this, and let's say, I don't know, 20 megabits per second. So mega basically stands for 10 to the 6. So 20 mega, which is times 10 to the 6 bits for every second. This is kind of an example. And kilo and others. Tera, you probably see this with storage devices. Let's say you have a storage device that has a capacity of, I don't know, 1 terabyte. So 1 terabyte is equal to 1 times 10 to the 12 byte. And every byte has, in it you can accommodate 8 bits. So this is kind of a different examples that you will see in real life. So when we talk about kilo, mega, giga, tera, and peta, these are for large values. So it's always good to remember this table, the engineering prefixes for large values. In a similar way, if we look at engineering prefixes for smaller values, in other words, values that are less than 1, you will probably see milli. So I don't know, maybe 3 millimeters, right? So what does 3 millimeters mean? It's really 3 times 10 to the minus 3 meters. So this is what milli stands. If you see micro, this is what it stands. This is a symbol of it. It's this representation here. This mu letter, Greek letter, and the mu stands for, or micro stands for 10 to the minus 6. Nano, this N for nano, 10 to the minus 9. P for pico, 10 to the minus 12, and F for femto, 10 to the minus 15. So if you want a value that is extremely small, something that is not 0. So these are not values less than 0. These are all positive values, but they are all values that are less than 1. So you could say something is extremely small and it has a range of femto. You would simply write F for that. F for femto, pico, nano, micro, and milli. So this is also very important to memorize, in fact, from these tables. Because when you look at different specifications and when people communicate as engineers, they will use these prefixes all the time. They would say this, we have a capacitor of 10 nanofarad. But what is nano? So 10 nanofarad stands for 10 times 10 to the minus 9 farad. So essentially it's 10 to the 10 to the minus 8 farad. But so basically what I'm trying to say is that engineering prefixes are used all the time. And if one forgets this table, then when you look at different values and you see it, it won't make sense. So it's very important that you memorize this, and you will use this across different courses here and also when you move to the workforce. So let's see different examples where we want to have a value in engineering notation. So let's say we are giving you this example and you have 0.47 M for mega ohm. So this is a quite big resistor. But if we ask you, is this value in engineering notation? So as we discussed earlier, engineering notation requires that the value here that you see should be a value, this is basically your A, it should be equal to 1 or less than 1,000. So this is not equal to 1. It's not 1 or above. So it would not work. And we know this is M, so that already leads us to believe that it is somewhat engineering notation. M is 10 to the 6. So we have kilo 10 to the 3, M, mega 10 to the 6, and giga 10 to the 9. So we know this is 10 to the 6. So if we drop by one other prefix, so we go to kilo, and then we multiply by 1,000. So we move by 3 digits. So 1, 2, 3. So it becomes 470 kilo ohm. Now this value here is certainly engineering notation, not this one. This value here is greater than 1 but less than 1,000. So that's checked. That works. And K is a multiple of 3. And that's checked. And that's a good engineering notation representation, not this one. Let's do another example. So if you look at this, this is 10,000 picofarad, right? So we talked about what pico is. So we said when we look at numbers that are smaller than 1, if you use milli, so milli is 10 to the minus 3. Micro is 10 to the minus 6. Pico is 10 to the its nano is 10 to the minus 9, and pico is 10 to the minus 12. So if you look at this value here, so pico is 10 to the minus 12, you look at this value here, does it meet the engineering notation, the requirement? Well, pico leads you to believe that it is a multiple of 3, it's 10 to the minus 12, so that's good. But this value is not good. It's 10,000. And we said in engineering notation, it has to be greater than 1, greater or equal to 1, or less than 1,000. And this is 10,000. So this is not good. So what do we do in this case? We could represent this as 10. And the 3, pico, we said this times 10 to the minus 12. We add times 10 to the 3. So when you multiply values with values that are similar with different exponents, you simply add them. So 10 to the 3 added to the multiply by 10 to the minus 12, that becomes 10 to the minus 9, and 10 to the minus 9 is nano. So this could be represented at 10 nanofarad. And this is in engineering notation. This value is certainly greater than 1, less than 1,000. And this is n, which is a multiple of 3. It's times 10 to the minus 9. And this is engineering notation. This is not engineering notation. Also, when adding or subtracting numbers with metric prefixes, it's important that you convert them to the same prefix to do the addition or subtraction. So let's see an example here. Let's say we're adding 10,000 ohms. And this right away, you know, it's not in engineering notation. You could just simply write it as 10 kilo ohms. You're adding it to a 22 kilo ohms. Now, how do you add these two? You first have to make sure that they have the same prefix. Here they don't have the same prefix. So one way to do that would be to put both of them in kilo. So this, we could write it as 10 kilo ohm, and this is an engineering notation, and this is 22 kilo ohm. This is an engineering notation. They have similar prefixes. Now we could add them, and the result is 32 kilo ohm. Let's do another example. So you're adding current. You have 200 microamp. Micro is times 10 to the minus 6 plus 1 milliamp. Milliamp is times 10 to the minus 3. Now, you cannot add them because the prefixes are not the same. You need to make sure that they're both the same. So if you want to represent this in micro, you need to multiply by times 10 to the 3. And if you multiply by times 10 to the 3, this becomes milliamp, but then you need to multiply by times 10 to the minus 3. And if you multiply 200 by times 10 to the minus 3 to get rid of this multiplication, it becomes 0.2 milliamps. So this becomes 0.2 milliamps. This is 1 milliamp. Now they have the same prefix. You could add them together and you get this result. You get your 1.2 milliamp. Is 1.2 milliamp in engineering notation? It certainly is. 1.2 is greater or equal to 1, and m is a multiple of 3, is times 10 to the minus 3, and therefore this is a good representation of the result. Is this in engineering notation, 0.2? It is not, but we did it just so that we can add these two together. 0.2 is not in engineering notation. This is less than 1, but we did it so that they have the same prefixes, and that's why. Whereas this is in engineering notation. So I hope you're comfortable with these different metric conversions and arithmetics that we did here. Now in here we provide you some definitions of what we saw here in the course. I'm not going to go through it. If you want to read it, please pause this video and go through it. And it continues on this slide as well. So here I'd like to show you some examples, multiple choice questions, and we'll try to go through them together very quickly. So let's say we are given this question. A number is written as 2.59 times 10 to the 7, and the question is, what is this? It is said to be in scientific notation, engineering notation, both of the above, or none of the above. So if you look at this, it's not a multiple of 3, so it's not engineering notation. Both of them would not be the case. So it's either A or D. Is it in scientific notation? It certainly is in scientific notation. The value is greater or equal to 1 or less than 10. And this is represented like this. So it is certainly A, scientific notation. It is also not D. So the answer is A. Notice that in multiple choice questions, it's always good to converge to the answer through elimination, not really by finding the answer, but really eliminating those that don't make sense and gradually converge to the answer. So we got it. It is A. Question 2, the electrical unit that is fundamental. Basically, when we say by fundamental, that is, it is part of the SI units, the System International of Units. Then we mentioned it: volts, ohms, and coulombs. All of them, amps as well. There are electrical units that we use, but the one that is fundamental, that is part of the SI units, it's really amps. So coulombs, ohms, and volts are something that you could find through the manipulation of different other SI units to converge to them. But the one that is fundamental, it's really amp. So the answer should be D. Question number 3, in scientific notation, the number 0.00056 is written as which one? So let's look at it. So we want scientific notation. This is not scientific notation. The value here, A, is greater than 10, so this would not work. This is not scientific notation. It's greater than 10. This would not work. Right away, without even looking at this, we know these C and D don't make sense. So we really are between A and B. If we want to represent it in scientific notation, we have to move to the right. So we move by 1 digit, 2 digit, 3 digit, 4. So it would be 5.6 times 10 to the minus 4. So the answer is B. It is not A. So as you notice, through elimination, we converge to the answer B, and the answer should be B. Question number 4, in engineering notation, the number 0.00056 is written as which one? So in engineering notation, we want something in the format of A times 10 to the B, where A is any number between 1 but less than 1,000. So they all work in that regard, so that's fine. In engineering notation, the exponent, the times 10 to the B, should be multiple of 3. 4 is not a multiple of 3, so we know A cannot be the answer. Minus 4 is not a multiple of 3, so we know B will not be the answer. Minus 5 will not be is not a multiple of 3, so we know C will not be the answer. So without even looking, we kind of converge to D. And again, we did this through elimination. Now let's just check. Does it work if you represent this in engineering notation? So if you work by 1, 2, 3, 4, 5, 6. So it will be 560 times 10 to the minus 6. And the answer is indeed D. Okay, question number 5. The metric prefix nano means which one? So if you recall, when we saw the prefixes for values that are small, we have milli, which is times 10 to the minus 3. We have micro times 10 to the minus 6. We have nano times 10 to the minus 9. We have pico times 10 to the minus 12. And we have femto times 10 to the minus 15. So nano should be times 10 to the minus 9. And so the answer is really C. So question number 6, the metric prefix pico means which one? So again, like we discussed before, we have milli, micro, nano, and pico. Pico should be minus 12, and the answer should be D. Question number 7, the number 2700, so 2700, M for mega and W for watt, 2700 megawatt can be written as which one? Well, first of all, before even answering this, is 2700, 2700 megawatt in engineering notation? So the mega leads us to believe that part of it is in engineering notation. There's a mega, so we know that's a multiple of 3. So kilo is times 10 to the 3. Mega is times 10 to the 6. Giga times 10 to the 9. So this is times 10 to the 3. But it is not in engineering notation, because for engineering notation, we expect the value here, the A, to be less than 1,000. And this is not less than 1,000. So let's see, nonetheless, which one does it equal to it? So they all have representation in terms of 2.7. So we know we could move to the right, rather to the left, by 3 digits. So by 1 digit, 2 digit, 3 digit. So we could represent it as 2.7 times 10 to the 3. And we have a mega. Mega, we said this time 10 to the 6 times 10 to the 6 multiplied by times 10 to the 3. That becomes times 10 to the 9. So this should be 2.7 gigawatts. So the answer should be B. So question number 8, the value 68 kilo ohm is equal to which one? So let's first of all look at this. Is 68 kilo ohm in engineering notation? Well, the A part seems like engineering notation. It is certainly greater than 1 and less than 1,000, so that works. And kilo is a multiple of 3, that's 10 to the 3, so this works. So this is certainly in engineering notation. Now let's see which of these answers really equals to this. So 68 is just 68 times k. K is times 10 to the 3. So you could in fact write it in scientific notation, and you'll get 6.8 times 10 to the 4. So this is correct. A is correct. What about B? K is 1,000, so you could also write it as 68,000 ohms. So this is correct. B is correct. M is mega, so you have kilo, mega, giga. Mega is times 10 to the 6, so you could move to the right by 6 digits. So it's 1, 2, 3, 4, 5, and 6. So it will be 68 with 3 digits, and that's also equal to kilo ohms. So this is also correct. So the answer should be all the above, D. Question 9, so the sum of 330 milliwatt and 1.5 watt is which one? So again, let's verify if each of them is in engineering notation. This is milli, so milli is times 10 to the minus 3, so that's engineering notation. This is a value 330, which is greater or equal to 1 and less than 1,000, so this is certainly in engineering notation. This too is in engineering notation. There's no prefix, and that's fine. That's also a multiple of 3. And the value is greater or equal to 1 less than 1,000. So they both independently stand in a standalone fashion are engineering notation. Now the question is, what happens when you add them together? So if you add them together, one way would be to, you have to make sure that the prefixes are the same. The prefixes are absolutely the same in order for them to be added together. So this is in watts. You could certainly change this to watts as well. So to change it to watts, you could get rid of this times 10 to the minus 3, and you could in reality write it as 330 times 10 to the minus 3. 330 is in fact 0.33 times 10 to the 3, and this is times 10 to the minus 3, so this can really be written as 0.33 watts. So if you have 0.33 watts plus 1.5, that becomes 1.83 watts. So it's not this one, it's not this one, it's not this one. The answer should be D. Okay, so this is the last question. It's a bit longer as well, but let's go through it. So write the numbers with 3 significant digits. So we need to make sure that we have 3 significant digits. Now, if you see here, we have 1, 2, 3, 4, 5 digits, but we only want 3 significant digits. So in order to do that, the 1 could be dropped, and so that becomes 4 significant digits. The 4 can also be dropped because it's less than 5, and we could represent this as 3.24 in terms of 3 significant digits. So that's 3.24 in as the answer for this one. This one here, if we want to represent it in 3 significant digits, we need to chop it up to this point. So the 8 will go up, it becomes a 0, this will become a 7. The 7, you could round this one, so and you chop it here, so the answer would be 5.04. To represent this with 3 significant digits, you need to have up to here. The 7 would bring this one up, it becomes 8. The 8 will, you can round this one up, so it becomes 0.847. That's in 3 significant digits. This one here in 3 significant digits would be, so you want 1, 2, 3, so it would stop somewhere here. The 3 would be rounded, so we still have a 3. The 3 would be rounded, so we'll end up at 0.0712. This one here in 3 significant digits will be dropped. The 3 will be dropped as less than 5. It doesn't round anything, so you'll have 19.0. If you simply write 19, that's 2 significant digits. But if you write 19.0, that becomes 3 significant digits. Here, if you want to round everything, because you have to stop after 3 digits, and if it's 9, so you round them up, so you'll end up with 3, but then you need to add 2 zeros to get your 3 significant digits. This one here is 5. You round it up, it becomes 17.0, and that's with 3 significant digits. This one here, to have in 3 significant digits, the first thing you should do is, first of all, because it's a large number, it is not a number smaller than 1. It is significantly larger than 1. So what you end up, first you should do is perhaps represent it in scientific notation. And in scientific notation, you'll get 4.3227 times 10 to the 4. And now once you have it in scientific notation, you need to get rid of the extra digits. So you need only 3 of them. And therefore this could round this to 3. And this you could drop. So we'll stop at 4.32 times 10 to the 4. This one here in with 3 significant digits, again, it's a very large number. Change it to scientific notation. So we would write it as 1.598 times 10 to the 6. And then we need to chop it with 3 digits. So this will round this one up. It becomes 8. So the answer should be 1.58 times 10 to the 6. This one here with 3 significant digits, this would be dropped. So the answer would be 143. This one here with 3 significant digits, the 5 would round this one up. So it becomes 197. This one here with 3 significant digits, again, it's a large number. Bring it down to scientific notation. So we get 5.4024 times 10 to the 4. Then this is less than 5, doesn't make a difference. This is less than 5, doesn't make a difference. This is just a 0, so the answer should be 5.40 times 10 to the 4. So maybe I went quickly, but this is how we do it with 3 significant digits. So for us, when we do labs and when we do evaluations and so on, please always stick to engineering notation and also to 3 significant digits. Usually when we are in a lab environment and we're using different equipment, power supply, digital multimeter, oscilloscope, I always tell students any measurements that you get from an equipment, use 4 significant digits, but if you use paper and a pencil or simulation, you could suffice with 3 significant digits. So please don't forget, when you do anything in this course, engineering notation, and stick to 3 significant digits. So these are all 3 significant digits, but are they all in engineering notation? They're not all in engineering notation. So so you have to meet that condition. So this is engineering notation, yes, yes. This is not engineering notation. It's the value is less than 1. This is not engineering notation. This is engineering notation. Yes, this is not engineering notation. This is engineering notation. This is not engineering notation. It's not multiple of 3. This is engineering notation. It is a multiple of 3. This is engineering notation. Engineering notation. This is not engineering notation. So as a first step, change it to 3 significant digits. Then change it to one more step to engineering notation, and that's what we would want in this course. Thank you for your attention, and lecture 2 will be posted later on. Thank you.